Hi, I'm Niklas. I'm a developer on the MaterialX project. This is an overview of MaterialX ShaderGen, which is the shader generation system that is part of MaterialX. So if you're a developer wanting to integrate MaterialX to your own application or renderer, or if you just want to know more about this work, then you might find this useful. ShaderGen is a system and an API to help applications turn MaterialX data into render-specific shader code. So the goal here is to support many different renderers and architectures to make MaterialX transportable between applications, teams, and companies. The output is source code in a shading language, which is then compiled into executable code by a shading language compiler for each target architecture. The API has a core library and then separate modules for each different language backends. And we support both real-time viewports and offline production rendering. For example, we can output GLSL or MetalSL for real-time viewports, and we can output OSL or MDL for production renderers. We've tried our best to make the system pragmatic and easy to use. So for an application, it's a single entry point in the API where you call it with MaterialX material or an output that you want to generate code for, and in return you get shader code that you can compile and bind to your renderer. I should point out that it's not a requirement to use the system to implement MaterialX support in a renderer, but it's available to help you and to ease adoption, and it can at least be a good starting point and a reference to look at. But it is being used in many cases. So one example is for the MaterialX support in Hydra Storm. Another example is the LookDevX editor in Maya, where it's used for the real-time viewport and as well as for rendering with Arnold. It's of course also used by our built-in provided applications, the MaterialX Viewer and the MaterialX Graph Editor. So those apps are good examples on how to use the API. So let's have a look at the code and the API. So here I have the MaterialX code distribution inside Visual Studio. We have the MaterialX core library, we have the viewer application, the MaterialX graph editor application. We have all the different Python bindings. And then we have these libraries for the MaterialX ShaderGen system. So there's a core ShaderGen library, and then different libraries for the different backends, the different languages. Also note that inside here there are different flavors for some backends. So for instance, for OSL, we have the default standard OSL shader generator, but we also have a new one, and this is a quite new addition, the OSL network shader generator. I can talk about that more later. For GLSL, we have the default GLSL shader generator, but then there are some other flavors. So for example, the ESSL shader generator for WebGL. There's the Vulkan shader generator, and there's also one for WebGPU. And as you can see, it's derived from the Vulkan shader generator. So there's this inheritance and specialization that you can use to easily add new support for new shading languages, but also support for new targets or new flavors of existing shading languages. So let's have a look at some of the main core classes that you need to care about. So in the core library, we have the base class for all shader generators. So from the application side, this is the entry point you mainly need to care about. The generate function which you call given a MaterialX element, could be a material or an output in the MaterialX graph. you have to give it a gen context, which is basically the thread local storage for generation. And when this completes, you get a shader instance back. Let's have a look at that one. So this shader instance consists of one or more shader stages, which basically holds the generated code. So you can get the source code out as a string, and you can get all the different inputs and outputs and uniforms created on this stage. And then this is what you use for compiling your code and for compiling your shader and binding this to your renderer. So some other classes worth mentioning. We have the syntax class, which is the base class for syntax handling. So if you're adding support for a new language, for instance, you need to add a syntax for that language. It basically controls how data types are emitted and formed in this language, what the reserved words are in the language, which affects how identifiers are allowed to be generated, for example, how to emit values in this language, and basically everything that has to do with the specific syntax and how we are allowed to emit code in that language. And there's the shader graph class. So this is basically the internal representation of the graph inside ShaderGen. So it's a DAG that is created from the MaterialX description, basically. And this graph consists of shader nodes. So each node in MaterialX will have a representation for as this shader node inside this graph, with ports and inputs, of course, and all that. And there's a class called shader node impl that is very important, because this class controls how the code is generated for each node, for each shader node. And this can be done in a couple of different ways. So let's move back to the presentation. Now we'll talk more about that. It can actually be done in 4 different ways. So you can use an inline expression. You can use a function written in the target language. You can use a node graph that describes the operation performed by the node, or you can use a C++ class that emits code dynamically during shader generation. Inline expressions are useful for simple nodes where the operation can be expressed as a single line of code. So a typical example of this would be like a math operation, like adds and multiplies and all that. And then you write the operation in the target shading language directly on the implementation element in the source code attribute. And inputs can be referenced in this expression using double curly brackets. So here we have an example. We have a node def that defines the clamp node, the float clamp node. And then the implementation element here describes how this is implemented for this particular target, the OSL target. And here the simple inline expression is used. So we just call the OSL version of clamp with these respective inputs. If we need more than just a simple expression, we can write a function for the node's operation. On the implementation element, we then reference a file where this function is stored and the function name. The function itself is, of course, written in the target language, and the function signature needs to match the nodef signature. So here's an example showing this for the color 3 image node. It's simplified for readability, but you can see on the implementation element, we then reference the file and the function name in that file. And here's the file. So it's an OSL function sampling the image texture. As an alternative to using source code, there's an option to use a node graph as the implementation of a nodef. As with functions, the signatures needs to match. So the node graph and the nodef must have matching inputs and outputs. This example shows a checker node implemented as a node graph. And the big advantage with this method is that this becomes a target agnostic implementation in the sense that this works for any target. As long as ShaderGen knows about how to translate the nodes inside the graph, it can translate the graph to any target. Also note that all of these first three methods are 100% data-driven, meaning that you can add new custom nodes or new features to MaterialX without needing to rebuild any code. So these are the recommended methods to use for most cases. In some cases, static source code or node graphs is not enough to implement the node. The code might need to be customized depending on parameters set on the node or options set globally by the renderer. Or for a hardware render target, vertex streams might be needed to created in order to supply the data needed for the node's implementation. Another example is for light interaction in a surface shader and for BSDF layering. You might need to analyze the BSDF layer stack connected upstream in the graph and then evaluate this for each light source in the scene. And in particular for hardware and rasterizer targets, a lot of these things needs to happen inside the shader we generate. So in such cases, a C++ class can be added to handle the implementation of the node. And this class should be derived from the base class ShaderNodeImpl that we saw earlier. And the emitting code for the function definition and or the function call can then be done by overriding the methods on this class. These dynamic nodes also needs to be registered on the shader generator so it knows about the node, as can be seen here. For languages like OSL or MDL, only a single stage is required. Those shaders are much simpler to generate since all of the light interaction, BSDF sampling and light sampling and all that happens inside the renderer. So the shader just needs to describe what closures to call and how the closures are combined to form the material. So for them, we generate to the pixel stage that is always available. But for renderers using OpenGL or other hardware render API, you need to handle everything yourself in the shader. So normally you need at least the vertex stage and the pixel stage, and in some cases other stages as well. But by using these dynamic nodes, we can emit stage-specific code. So the methods that emit function definitions and function calls are then called multiple times by the generator, once per stage. And here's one example for the text chord node in GLSL, where we emit different code if we are called by the vertex stage or by the pixel stage. We also need to control what data to send into our stages and between our stages. The inputs authored in the MaterialX data are always created as uniforms on the shader, so they can be assigned values later. And with dynamic nodes, we can create additional variables needed. So for example, extra uniforms or geometry streams needed by a node. And we can then control how these are propagated between stages as well. The stage stores all the variables in blocks. There are predefined blocks for vertex inputs, public uniforms, private uniforms, and stage connectors, and new blocks can be created as needed. For agreeing with the application side what data to bind to each input, there's support for adding semantics to each variable. But for our existing generators, we use a default naming convention instead. So how our vertex input variables are named and what they should bind to. And all this is described in more detail in the developer guide. So here's an overview of the shader generation process. It can be split into two parts, the setup phase and the code gen phase. So first, the setup phase. The first thing we do is to create the shader graph. We convert the MaterialX data into the internal DAG. Then we can run optimizations on this graph. We don't have to do too much here because the produced shader will later on be compiled by compiler anyway. where a lot of optimizations happened, but there's a step here where things can be done if needed. We need to sort it, order nodes by dependency, and we validate the graph, checking for cycles. Then we create the stages needed by the shader, and we establish the interface, so the uniforms, inputs and outputs and all that on the stages. And then we can start the coding phase. So first we emit any type definitions needed. Then we generate all the function definitions. So from the static code, from the node graphs, from these dynamic nodes, we generate all the function definitions we need. Then we emit the shader signature with inputs and outputs, and we emit the shader body with all the function calls for each node in the DAG. And then we produce the final output result. And normally a single monolithic shader is generated, started from the given material and including any texturing and pattern nodes upstream. But if this is not appropriate for your system, the generator can also be called on output elements at any point in the MaterialX graph and generate code for subparts. So it's then up to the application side to decide where to split the graph and to assemble the shader code for subparts after it all has been generated. And one example of this is the new OSL network generator. It first generates OSL code for each individual MaterialX node. These are then compiled into small executable units called OSOs. And then the MaterialX graph is translated to a network of these OSO shaders that an OSL renderer then can consume. So finally, let's take a look at an example. So here I have a material loaded in MaterialX View. It's a version of standard surface. And now there are keyboard shortcuts to export the shader to a file on disk. So if I press G for GLSL, the GLSL shader running in this viewer is now saved to disk. There are also shortcuts for OSL. So pressing O for OSL, I get the OSL source, and also MDL, pressing M for MDL. Now we can take a look at these files. So let's look at the OSL file first. So here is the OSL file with all the function definitions generated. In the bottom, we have the main shader body. Here, so this is the signature with all the uniforms and the shader body. You can see there are a couple of functions here. This is the function for the tiled image node. I can tell by the ng here that this was generated from a node graph. Same thing with this one for some color space conversion. And the same thing here for standard surface. So standard surface is actually implemented as a graph. And here's the function generated from that graph. All the various math things going on. And we can have a look at all the different closures. So it's basically a mix and layering of closures. So this is a closure, an OSL closure. Here's another one. As I discussed earlier, sampling these and evaluating these happens inside the renderer. So here the shader is only responsible for mixing and layering these. Okay, so we can compare this with the GLSL version. So here we have two different stages. We have the vertex stage and the pixel stage. So let's look at the vertex stage first. We can see the different uniforms and inputs generated. And down here, a very simple vertex stage, just converting the normals, tangents, and text chords and positions that we need. And if we look at the pixel stage, it's pretty similar to what we had for OSL, but with the big difference that here we have to take care of all the light interaction. The same as before, and the main function, the main body, calling the standard surface node graph here. But this one is different because now we can't just call closures that are evaluated by the renderer. So instead we have to handle this ourselves. And this is for a forward renderer, so we have an explicit light loop here. As you can see, we loop over the light sources. We evaluate the BSTEF layer stack for direct lighting, what that is, and then for environment lighting or indirect lighting, things happen here. We add emission, transmission, and then compute the final result. For more information, you can check out the developer guide available on the MaterialX GitHub. Also check out the Academy Software Foundation Slack. There's a MaterialX channel, and you can reach me there, or you can just send me an email. Thanks for listening. I hope this was useful.